Are you ready for the practical?
Mine is the big one.
Could you talk to me? Oh, I thought you were putting the guy walking by.
It was really easy. Like, I mean, if like everything that basically was on that review was from the class. Like, if you knew the review, you knew the practical. There weren't like sneaky trick questions.
Good.
Stuff like that.
Okay, thanks.
Like your diet? Who's like, oh, that's how I was like,
And then yeah, so I'm sitting between you and I have no idea what that is.
oh yeah.
Like you call next to me and then on the outside I'm going to do the same. There's no way. And then this morning Sandra wakes up and she's like,
That's what happened to me. I think it's gone. I think it was like one of those like 3-day things.
yeah. I could feel the air rush by me. It was bothering me so much.
That happened to me yesterday. You like laid down and like crossed his arm, and like it just
Went
went
straight
all
under?
over my hand. And I was like, ah! And like 5 minutes later, I was just like, I was like, I don't know if that's doing anything, but I don't like that.
It got like, and I had my head down, so it was like a rough choice. I think, and I sat up right away. I was just like, well, you can go down today. It was real bad. But yeah, I was thinking starting a little bit.
I haven't decided. Oh, I'm saying this, but I haven't decided whether or not I'm going to take it. I guess it just depends on how I understand. Because the only time I would be able to take it is between strictly school and class.
Yeah, I want to.
Yeah.
I started at like 8, then I haven't.
Well, it starts at 8:30.
8:30, but
It's
still
8:30 to 10:30.
Oh, it's pretty much it.
Yeah. Because that's the thing. It's the same allotted amount of time, so I don't know if I'd be able to just do it. I might not do it.
Yeah, I really want to know it by Thursday, so like, do it.
Yeah.
But I also wouldn't mind the extra time. The other reason I kind of want to do it Thursday is in the morning, like when I'm starting everything. Yeah, like connected to my brain. So I kind of like the idea of doing it after I really like it.
I mean, mine would make it so it's equal. I was like, okay.
Probably have to do like a night. I might actually have time. Everything.
Yeah.
I think it just starts with. Yeah. I think everything's done. Okay.
Ortho, substitute 1 and 2, I say meta. Substitute 1 and 3, I say para. Substitute 1 and 4, OMP. Now sing with me. Ortho. Substitute 1 and 2, I say meta. Substitute 1 and 3, I say para. Substitute 1 and 4, OMP. Now sing with me. It's fun to sing about my benzene ring. It's fun to sing about my benzene ring. Substitute methylene and you have toluene and H2 for aniline. It's fun to sing about my benzene ring. Fun to sing about my benzene ring. NOH propanol, phenol's missing an H, NO2 makes nitrobenzene. Benzene is unusually stable, it's cyclic, planar and hexagonal hybrid, with 2 resonance structures, of course, it's conjugate. created Huckle. Gave us 4 plus 2, he said in his integers that you choose. So just count up all the pi electrons. 2, 6, 10 are aromatic.
Here comes.
Just like my benzene ring. It's fun to sing about my benzene.
Put your head down.
Substitute methylene and you have toluene and H2 for aniline. It's fun to sing about my benzene ring. Fun to sing about my benzene ring. NOH for phenol, phenol splits in an H, NO2 makes nitrobenzene. Listen, make a bromobenzene at Br2 and FeBr3 for add chlorine. Cl in place of bromine.
Got this in a minute and a half.
Right. I don't know if we'll get quite that far this semester, but anyway, now we're trying to figure out orthometapara. That song will go through your head.
6,000.
Can you believe it?
Approaching 7,000.
Should be more than that.
I'm getting to.
Say, that's right. Are you doing para or are you asking a question? All right. So there's another one which we'll save for Monday. I know, but it's really that's a good one too. Okay. All right. So back to a few things. So I realized that I handed out the Keklier article, but then I really never said anything about it. And so, right, I did hand this out. Yes. Okay. I don't have a stack of them. This is something for you to read over Thanksgiving break. Keklier is a famous scientist, and he is actually the person who discovered basically the idea of conjugated or delocalized electrons, right? When you think back to the 1800s, what are the things we knew? We might have known there were 6 carbons and 6 hydrogens, but we didn't know how everything was arranged, and we didn't know how these electrons were delocalized, and he had a dream, not as good of a dream as some other people, but anyway, he had a dream about a snake catching his tail, and that sort of made him think, oh my God, that's really how this is happening. So, you too can have good, fun dreams. I know other psychology people are like, yeah, that's not what a snake in the dream is about. Anyway, this is kind of funny.
You waiting for the laugh?
Yeah, I am waiting for laughter, but it's not coming, so I'm just going to stop. So, remember that there's an extra credit seminar tomorrow. So the seminar is in this room, 12:45. If you come and you sign the piece of paper, you get the 4 extra credit points. That's what you need to do to get that. Let's talk about if you can't make it to the seminar, because I know there's a field trip that's occurring tomorrow. What will happen if you can't make it to the field trip is that on Friday, I will tell you about a paper that I want you to read. Then you need to read the paper and write a 2-page summary of the paper and turn that in by a specific date, all to be determined after the seminar. So that is, if you cannot make the seminar, you can still get extra credit points. I would highly suggest that if you can make the seminar, it's a far easier way to get 4 extra credit points. But I realize that some of you will be out of town, so you can still do that. Okay? And then as far as the quiz is concerned, I did send you different times. So remember that the quiz times have changed because of all the things happening on Thursdays, which means the quiz is still from 8:30, but it ends at 5 on Thursday. So it's from 8:30 to 5 on Thursday, or 8:30 to 10 on Friday morning. So if you can't make it during the Thursday times, hopefully you can make it during the Friday times. And if you can't make any of those times, I would have hoped that you would have sent me an email by now, And as I did not receive any emails, I'll assume that those times are fine for everyone. Right? You are free to take it either Thursday or Friday. It doesn't matter to me, but you do, of course, need to take it. What will the quiz cover? Are there any questions about that?
Can you just list it one more time?
The times?
No, like what's the topics
Yes,
of the
What, pardon me?
the topics of the quiz?
Yeah, that's what I'm going to do right now.
Yeah.
So any other questions about the time? All right, so what's on the quiz? All of the reactions that we've done this far this semester are on the quiz. So that's basically all of chapter 8. And then, of course, the HBR addition to an alkene was chapter 7. So it's all of the reactions, the ones that were on the last test as well as oxidation. Oxidation is really the only question that was not on the reaction that was not on the last test, but we're doing all reactions of alkenes. All reactions of alkenes are on the test. Chapter 13 is on the test, not chapter 13, but yes, chapter 13, which is really C13. So C13 NMR is on the test, and again, the type of question I will ask you is, here's a molecule, how many carbon peaks would you see in the NMR spectrum? Here's a molecule, how many peaks would you see in the depth 90 spectrum? Right, I can ask you any of the depths. I'm not going to ask you to put a molecule together, it's just going to be a simple figure out how many peaks there would be kind of question. I can also ask you, here's a molecule, circle the carbon that's most upfield. Here's a molecule, circle the carbon that is most downfield. So you don't have to know exact chemical shifts, but you have to know if I have a carbon bound to an oxygen in my molecule, approximately where on your spectrum is that? And then the other way I can ask you the same question is to say, here is a C13 question, here are 4 choices. Which molecule? That's a multiple choice way to ask C13 questions. Here's a spectrum, here are 4 choices, tell me what it is. So those are C13s. Resonance is on your test. So make sure you know how to draw resonance forms. And the last thing that is on your test is nomenclature. So nomenclature of aromatic rings. You have to know common names, you have to know how to name any of these things. We ended Monday's class with aromaticity, but we didn't really get far enough to be able to ask an interesting question on it, so the whole concept of is a molecule aromatic or not will not be on this quiz. We're going to continue it today, but it's not going to be on your quiz. It will be on your test. All right, so any other questions about quizzes? Okay. Is anybody expecting to take it tomorrow morning? 8:30. Excellent. Yes, be ready. Just want to make sure I don't cross it. Was. We can take it to the stand. All right, you'll be ready. All right, so what is the name of this molecule?
3-ethyl 5-fluoro nitrobenzene. No.
Aniline.
Why is it switched? Okay.
Because I heard someone say 5-fluoro first. All right, how's that for a correct name? Right, 3-ethyl 5-fluoroaniline. Remember, this part of the molecule is aniline. And this is the number 1 carbon, and you could choose to go this way and get 3 and 5, or this way and get 3 and 5. And why was the ultimate choice in that direction? right? Because if you're going to get the same sum, right, if you get a tie either way, then go alphabetically. What's the next? What's the first substituent? So I went 3-ethyl for fluoroethyl. Okay. Ooh. All right. So we ended class by talking about substituted cyclopentadiene. And we looked at that, versus that. All right, so you start with cyclopentadiene and you somehow remove a hydrogen. You either take the hydrogen and its electrons, which means you would get this. You take the hydrogen and its one personal electron, you would get this, which is neutral. You take the hydrogen without its electron, so as H+, you would get this. And so the question is, what is the question? The question is, are any of these aromatics? So the real question is, what are the 3 requirements for something to be aromatic? Needs to be completely conjugated, needs to be planar, and it needs to have the Huckel number of electrons. Okay? So I'm going to tell you these are planar. So you can assume planarity. Is this conjugated? Is there a p orbital on each vertex of this? Yes. Right? So it's conjugated, it's planar. Now the important question, how many pi electrons does this have? I hear all kinds of numbers. Right? The number of pi electrons, how many are here? 2. How many are here? 2. How many are here? 0. So the number of pi electrons that that particular cation has is 4. The number of pi electrons in this system, pi electrons, is 5. The number of pi electrons here, 6. Remember, a negative charge is a pair of electrons. One of them belong to the carbon, one of them is extra, which is why it's only -1. It's 2 electrons. And therefore, if I ask you which of these species is aromatic, you will tell me that that one is aromatic because it has the Huckel number of electrons. And all that's really telling you, which is sort of a lot, is that for this molecule to go to this ion, right, so you're telling me that this is aromatic, i.e. this is very stable. So this neutral molecule, which is also very stable, not because it's aromatic, just because it's neutral, right? But this neutral molecule could be inspired to become this because it's becoming something very stable. Normally you wouldn't think anions or cations are all that stable. This one happens to be stable because it's aromatic. But to get from here to here, right, how did this go from here to here? Well, it lost a proton, right? It lost a hydrogen, H+. This hydrogen lost a proton. And so, if you look at this, what kinds of molecules go from here to give you something in an H+? Acids. Right? Aren't acids H+, something that will give you an H+ as an acid? If you put HCl in water, what do you get? H+. Right? So you think of it as an acid. So you think of this as an acid. You think of this as an acid. You might even think of this as an acid. It is. Right? Well, this, even though this looks nothing like being an acid, is actually reasonably because you're forming something stable. Right? So things that don't look acidic actually turn out to be reasonably acidic. Now, again, this is acidic for an organic molecule, right? We'll look a lot at acidity next semester. These things are truly very strong acids, right? You put those in water, you instantly get lots of H pluses. This is acetic acid. Anybody remember, is acetic acid a strong acid or a weak acid? It's a weak acid, right? It's not really very, you put this in water, most of it is still acetic acid like this, not the anion and H plus. So that's probably our strongest organic acid. And so we're still going down as far as acidity. This isn't anywhere near as acidic as HCl. I want to be very clear about that. But for an organic molecule, this is a reasonably acidic species because you get to something that is stable. If you didn't get to something that was stable, this hydrogen has no reason to come off, and therefore it wouldn't be acidic. Right? So that's really where acidity comes into play. All right, so very quickly, if I gave you cycloheptatriene, and I asked you to draw me the carbocation version, the radical version, or the anion version of this, I want you to draw the one for me that is aromatic. Right? So do something with one of these protons, just like we did for the 5-membered ring. Do it for the 6-membered ring, but draw the one that would be aromatic. I'm not saying it's acidic. I'm simply saying draw the species that would be aromatic. Put a plus, a radical, or an anion. Right? Which one's going to give you the right number of electrons? Well, how many do you already have? You already have 6, and that's a Huckel number. So if you give it any more, it's going to not be aromatic. So if you don't want to give it any, then it has to have the positive charge. So in this case, the carbocation is aromatic. Okay? Just getting you to think, sometimes you have pluses, sometimes you have minuses. And unless you have 2 different radicals, it's going to be hard to have an odd number that fits 4n plus 2. Okay, so that's aromatic. Questions? That's not aromatic, that's aromatic of anions. All right, so now let's get to where it becomes even more interesting. What if we have heterocycles? How would you define a heterocycle? And I couldn't hear all of that, but what you want to do is you want to look at your cyclic system and see that somehow in that cyclic system, at least one of the atoms is non-carbon. So a heteroatom or a heterocycle to an organic chemist is not necessarily the number of vertices that you have. Doesn't matter if you have 5 or 6 or 7 or 8. It matters that one of those vertices is non-carbon, right? Because you know all we really care about is carbon. So if you have a heterocycle, that means you actually have one atom that is not carbon. For example, right? I have a cyclic system. One of my vertices is not carbon. So this would be defined as a heterocycle. It doesn't have to be nitrogen, it can be oxygen, it can be phosphorus, it can be sulfur. It just has to be non-carbon. Okay. So this is an example of a heterocycle. It doesn't have to be that. Here's an example of a heterocycle, right? It's a cyclic system with an atom that is not carbon as one of the vertices. So we're not going to worry about this one right now because we're talking about heterocycles in terms of aromaticity. Yes?
You said that nitrogen could be an oxygen. Wouldn't that violate oxygen's bonding rules?
Right. So I just simply meant that not this exact nitrogen, but one of the atoms. Yes.
Okay.
You can. This one, in this exact case, you can't have oxygen here, right? Because that would violate that. But in a heterocycle in general, if the atom can be an oxygen, there can be multiples of it, things like that. Yep. Actually, are you? Oh. Okay. So we have this molecule. This molecule is known as, it's not benzene because it looks like benzene, but it actually has a nitrogen as one of the vertices. Its name is pyridine. Pyridine happens to be a very common base. Anybody ever work with pyridine? You wouldn't forget it if you did. Right? It's really a stinky molecule. It looks very simple, but it has a nasty smell. Right? So you know when you work with pyridine. So here's pyridine. C5H. What's the molecular formula? C5H5, right? There's a hydrogen, 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 no hydrogen. What's the hybridization of this carbon? sp2. What's the hybridization of this nitrogen?
SP.
What does this nitrogen have that I've not shown you? A pair of electrons. So when you look at this nitrogen and it's sp2 hybridized, what are in this nitrogen's sp2 orbitals? 2 electrons are in one of them. What's in this one? Bond to a carbon. What's in this one? Bond to a carbon. Right? So bond to a carbon, pair of electrons, all in the same plane. The p orbital is in and out of the plane. It overlaps with the p orbital here. Is pyridine aromatic? It's planar. Is it completely conjugated? Is there a p orbital on each one of those vertices?
Yes.
Yes. Is there the Huckel number of electrons?
No.
Say that louder. In the p orbitals, remember we're talking about Huckel number of electrons in the p orbitals, in the delocalized orbitals. How many are here? 2. How many are here? 2. How many are here? 6. 6 is a Huckel number. Yes, pyridine is aromatic. These electrons are not in this orbital here, right? They're not in the pi system. These electrons are out here where the hydrogens are. Right? If this atom is nitrogen, this is a pair of electrons, not a hydrogen. But it's in this plane, not the p orbital plane. right? At most, an atom can only give 1 or 2 or 0 electrons. You can't put 3. This nitrogen can't give 1 to form the double bond here and this pair of electrons. That's 3 electrons in 1 orbital. That can't ever happen. So pyridine is aromatic. It's aromatic, sp2, 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 really no questions. Or are there? Okay, so what about this molecule? This molecule is known as pyrrole. Is pyrrole aromatic? Okay, so I guess the first rule is it planar? I'll tell you it is. The second rule is it completely conjugated? Right, and you're going to tell me that this nitrogen is what hybridization? Right, you probably would have told me that it was sp3 hybridization because it has a pair of electrons and a bond and a bond and a bond. So 3 bonds and 1 pair of electrons usually means 4 things. I spread those 4 things out, sp3 hybridization. And that was true at the beginning of the semester. But now you have something else to consider. Remember, things are only sp2 or sp3 or sp hybridized so they can spread their electrons out to the best way that's possible for the molecule. Well, sp3, great. What if this nitrogen is sp2 hybridized? If this nitrogen is sp2 hybridized, then sp2, 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 where's this pair of electrons go? In a p orbital. If I have a p orbital here on this nitrogen with 2 electrons, p orbital, yes or no?
Yes. Yes.
Okay, so if this is sp2 hybridized, now I've satisfied the conjugated question. Right now it's completely conjugated. If this is true, then the last question is, if this is sp2 hybridized, how many electrons are now in this pi system? 6. 2, 4, 6. So now there are 6 electrons delocalized over 5 atoms. Is 6 a Huckel number? Yes, let me go back and ask you this question then. Is this molecule aromatic? Yes. And if it is aromatic, there is only one answer to this. What's the hybridization of this nitrogen? sp2. So now, from now on, you have to check and see, is it to the advantage of the molecule for this nitrogen to be sp2 or sp3? When it becomes sp2, the molecule becomes aromatic, then yes, it is sp2. If it goes to sp2 and that makes the molecule not aromatic, then it doesn't go to sp2 and it remains sp3. Right? So this nitrogen is going to take one for the team if the whole molecule can drop in stability by becoming aromatic. But if it doesn't become aromatic by being sp2, then it won't do it. Right? It only changes its hybridization if the molecule can become aromatic.
So is it losing those 2 electrons then?
Well, so is it losing those 2 electrons? Right? And the answer to that is, in a sense, it is losing those 2 electrons because they're no longer isolated on that nitrogen. They're now part of this conjugated system. So those 2 electrons no longer belong to the nitrogen. They're now part of this whole system. They belong to the molecule. Right, so heteroatoms can become aromatic. You just have to figure out what their hybridization can be. And remember that it will only rehybridize to something if that is helpful. So, a typical question. One typical question is, I'll draw a bunch of molecules, are they aromatic or not aromatic? Right, you know the 3 rules, you have to apply them. Another question that I can ask you, particularly about heterocycles, is what is the hybridization of the atoms? And you have to be able to tell me sp2 and sp3, but I know in your brain that you've already had to figure out, is it aromatic if I do it this way or not? Right, so you have to do that now. I can ask you how many electrons does this nitrogen contribute to the pi system? So I could ask you, how many electrons does this nitrogen contribute to the pi system? 2. How many electrons does this carbon contribute to the pi system? 1. Right? 1, 1, 1, 1, 2, that gave me 6. How many electrons does this nitrogen contribute to the pi system? 1, right? It's hard to see here, but remember, it's part of this double bond. Oh, yeah. Right, so it gives 1. Right, it gives 1. Okay. What about... What about this?
Would it say sp reorbitized if it wouldn't make it aromatic?
Mm-hmm. Yep. Right. If it doesn't make it aromatic, it goes back to. It always goes to what's most stable for the molecule. So by changing to sp2, if that makes it aromatic, then that's most stable for the molecule. If changing to sp2 makes it not aromatic, then it's most stable to remain as sp3.
So those 2 electrons are only contributing to the system if they're in the same plane, the same orbital?
If they're in the pi system. Right, those 2 electrons are only contributing to the pi system if they're in that p orbital. Right, so in this case, not in this case, in this case, right, when we add pyridine, the 2 electrons here are in the same plane that this hydrogen is, right, the plane of the board. This nitrogen's using its p orbital to form this double bond. So they're not included here, but they would be included here because this hydrogen is in the plane with all of these other hydrogens, and the p orbital has the pair of electrons there. Okay. All right. This molecule is known as pyrimidine. This molecule is known as purine. Oh, who might start to recognize these? Right, so let's, before we even go to why these are useful, is this molecule aromatic?
Yes.
Yes.
Yes. How many pi electrons are there?
6.
6. How many pi electrons does this nitrogen contribute? 1. How many does this one contribute?
1.
1. Where is this pair of electrons here?
In the plane.
It's in an sp2 orbital that's planar with the board. So that's aromatic. Both of these are aromatic. Right? When I look at this molecule, how many? Remember, I'm telling you this is aromatic. Right? And if I'm telling you this is it, well, when you flat out look at this, you would say p orbital, 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 p orbital. Oh, is there a p orbital? Right? So it almost looks like it's not conjugated. If it's not conjugated and there's no way to make it conjugated, then it can't possibly be aromatic. But you could hybridize this nitrogen to be sp2, and if it's sp2, then that bond, and that bond are all in the plane, and my p orbital contains 2 electrons. So how many pi electrons does this? And I'm telling you it's aromatic, so you know this is sp2 hybridized. How many pi electrons are in that molecule? 10. 10. Yep. 2, 4, 6, 8, 10. This pair of electrons in the plane, in the plane, in the plane.
In Spain.
Pardon me? Okay. All right. So, why could these suddenly become molecules of interest to you? They're related to your DNA bases, right? The base structure of your DNA bases, DNA/RNA bases, are pyrimidine and purine, right? So which one has the pyrimidine? Oh, where am I? Right, so how about we write them down? A, G, C, T, and what about RNA? U. RNA. Do you remember which one's here?
C.
It is C. I mean, think about it this way, right? A binds with T, C with G. Okay, and then U substitutes for which one of these?
C.
Okay. So for those non-biologists, right, uracil is an RNA base that takes the place of thymine. I mean, help out a little bit. Okay. So anyway, just showing you again. The interesting thing to do, and what I was going to have you do for homework, is to actually look up the structures of these and show that they really are aromatic. Right? So why don't you look up the structures of these? They obviously come from here, but they're slightly different in the form you see. Yeah, yes. It's not hard, right? You can Wikipedia them, right? And just write down their structures. Okay? So then you can look at them. Because they don't look exactly like this, but they are pyrimidine-based or purine-based. Now, they are your DNA bases, and they are aromatic. Why is that a good thing? Because they're stable. Right? If your DNA bases are something that makes up who you are, is not very stable, then who you are one day is probably not who you are the next day. Right? You want things to be stable. You want these to be in your body. You want them to not react with things. You want them to be able to hold structures together. Right? You're based on these bases. It's important. And aromaticity is important. Because without them, you wouldn't know who are you. I did that really for Rachel. How was it? Amazing. How was Roger? Oh, my heart dropped. 12. Okay. The rest of you can be filled in on that. So, right, I'm not singing the CSI song, but I sort of am. All right. So, let's actually, I'm going to draw one of these for you. I'm going to draw. Let's go with all right, so this happens to be Duracell, right? Nobody ever pays attention to RNA, so we'll do it. Here's uracil. Here is pyrimidine. Would you have said that these two were structurally related? Yeah, maybe some of you, yeah, some of you know, right? There's a six-membered ring. There's nitrogens in the same places, right? It has substituents on it that are non-hydrogen. Right? They're actually very closely related to one another. You know this is aromatic. You know this is your RNA base, which needs to be stable. So the question I'm asking you is this molecule aromatic? Okay, well, the right answer to that is yes, because that's what we've been talking about. But now, how many pi electrons are there? There are 6. Okay. So there are 6 pi electrons. It is aromatic. What is the hybridization of this nitrogen? sp2. What is the hybridization of this nitrogen? sp2. So at least now we have a p orbital every place. So there's 2 electrons. If this is sp2 hybridized, what must be in the p orbital? 2 electrons. So there's 2 there. There's 2 there. This is sp2, and then those 2 electrons are in the pi orbital. So I'm at 6 already. What am I doing with these 2? Right, so here's where you have to apply your knowledge. 6 is the right answer. Right, but what do you know about carbonyls? How are they polarized? They're polarized towards that oxygen, which means that these pi electrons are much closer to that oxygen than they are to that carbon. And if the pi electrons are closer to that oxygen, what does this look like? How many electrons do you think are in the p orbital here? I'm sort of hearing mumblings, but I'm hoping somewhere along the line you'll tell me 0, right? Because you have 6. I told you there were 6. And you have 2, 4, 6. So that only leaves 0 in these, right? So think about your carbonyl. Some of your homework questions are like this. If this carbonyl, and remember, these are pi electrons that can move. Polarization, these electrons are moved towards this oxygen. If these 2 electrons are moved closer to this oxygen, that's almost like there's a carbocation there. There's not really a carbocation there, but these electrons have moved so much closer to the oxygen that if that were a carbocation, this would be an empty p orbital. And what's happening up here? Same thing. These electrons are being pulled towards that oxygen. So this carbon here is as if it has no electrons in it, no pi electrons. So you have 2, 4, 0, 6, 0. Completely conjugated? Yes. How many electrons are in the pi system? And here's the key piece. It's of the ring. We don't care about what's happening out here. Right? Of this cyclic system right here, these 6 atoms, there are 6 pi electrons. Right? So you have to pay attention to a lot of things. You have to pay attention to polarities. Right? You might not have expected this, but if you now know that it's aromatic, then you have to look closely at your molecule and say, what can be happening here? What can be happening is that's sp2 hybridized, and these electrons are pulled away from the ring. So it's as if this carbon is contributing 0 to this ring. Good? Got it? 100%? Excellent. Well, now you are virtually finished with chapter 15. All right, so the last thing, virtually I said, virtually. We have one more thing to talk about.
Nice try.
And the one more thing we have to talk about I was told something. Let me. Some of you may think of it like this. Polycyclic aromatic hydrocarbons. Those of you who are in the environmental field, what do we call polycyclic aromatic hydrocarbons as a shortcut initial name? There you go. Oftentimes you will see that organic contaminants in the environment are PAHs. Right? That quickly stands for polycyclic aromatic hydrocarbons. The one rule that I'm going to put up here about the polycyclics versus the monocyclics. Right? What are the rules for a monocyclic substance to be aromatic? Conjugated, planar, Huckel number of electrons. If you have a polycyclic hydrocarbon, the one rule that goes away is that it doesn't have to have the Huckel number of electrons. So they have to be conjugated, and they have to be planar, but you no longer have to worry about how many electrons are in that system. Right, that's the only rule that's different. You know two PAHs. What are they? Oh, you know several actually. Yeah, purine wouldn't be considered a hydrocarbon because it has a nitrogen in it. So you know this molecule as naphthalene, and then if I add another ring here, anthracene. Right, those are some of the ones that you run into. You also, and you don't have to know any of these, but they're pretty. Right, so some of the other polycyclic aromatic hydrocarbons that you see have these structures, right? You can put 4 in a row, you can put 5 in a row. If you look at all of these, you will see that they are all, in fact, completely conjugated. They don't necessarily, many of them have Huckel number, but many of them don't. And so I'm never going to ask you, well, except for these two, right? I'm never going to ask you these. I just want you to see, because these are the sorts of molecules that you're going to see. They persist in the environment. When they get into the environment, why? Because they're very stable, right? And they're not very water soluble, right? Hydrocarbons don't tend to be water soluble. So if you get them somewhere, water's not going to wash them out. Now we're finished. Again, these things are it is with an A, anthracene. If I had it with an E before, yeah, it's anthra, not anthracene. Yeah. And naphthalene does have that extra P.
I have 2 questions. So,
Yes.
in these, for example, why would they just like define it like would it still be
Yep, because it's still a bond.
okay. And that means the one word on the